Alex is going to talk about a selection of agent-based behavioral models in economics.
Thank you for inviting me to give this talk. It's a bit more like an intro talk that we've seen before, a summary or selection of some models that I wanted to talk that may be of use to some of you. Well, first, my affiliation is School of Economics and CEDEX. CEDEX is Center for Decision Research and Experimental Economics here at the University of Nottingham. And our research is to study human decision-making using both theoretical and experimental survey methods, focuses mostly on behavioral economics. But some of the topics that we studied, in particular, rule compliance, perhaps something that came up in the discussions, so maybe of interest to some of you. We also, in the research of the research center, we also do applied research, and one of the postdocs, for example, works on carbon emissions, how to motivate people to reduce their carbon footprint. Okay, maybe it's of interest. Now, what I actually wanted to present a bit of discussion of how agent-based models used in economics. There was a recent survey paper in Journal of Economic Literature that discusses the use of agent-based modeling in economics and finance. They present ABM as a methodology to represent behavior of individuals to study social phenomena. A summary of what it does, all of you know it, but we have software agents that interact in an environment, economists in economic environment. The agents use some rules of behavior that are inspired by observed human behavior, but not exactly corresponding to it. And the focus is typically on the aggregate outcome of agents' interactions. The authors of this survey list the growing use of these models in various subfields of economics. What I will present is actually my own idiosyncratic summary of selection of models like this. And I will start with a model that most of you know or seen many times, the sharing segregation model, originally appeared in Sociology Journal, where we have agents on a two-dimensional grid. They are considered happy if the proportion of neighbors of the same type as them is at least a certain number, and they can move to a random empty space if they are unhappy. And I wanted to present this model because most of the agent-based models that I've seen in economic analysis actually follow these two important steps, model these two important steps. What is the utility of agents? In this case, agents are happy or unhappy, depending on their neighbors. And what can they do to improve utility? In this case, they can move to a random empty space, unhappy. They don't, in this model, don't optimize completely. They just try to become better, but they don't make an optimal move. They behave optimally in a very limited sense. Now, you probably know that in Schelling's model, a segregation between types of individuals emerges even if the preference for your own type neighbors is relatively mild. For example, P equals 1/3. And the reason I wanted to present it on my own computer is that I actually have a very simple simulation of this model that I use sometimes for teaching, to demonstrate to students how it works. So here you have a two-dimensional grid. You can initialize it with random population of red and blue individuals and some empty spaces to move. The happiness rule is that agents are happy if the proportion of neighbors of the same color as them is between 1/3 and 1. And they can move to a random empty space if unhappy. So one can run these models. This particular model, agents move around, and you can see that from a relatively mixed population, the grid converges to more separate red and blue clusters. You can do it many times, and it would happen almost every time that it would be separate clusters. And you can also modify parameters easily. So, for example, if you want to study at what point this parameter will not lead to segregation, you can decrease it. Specialize run, so it's kind of relatively smaller movement, and for mixed population. And sometimes I even demonstrated to students that you can consider other preferences in this model. For example, preferences for variety. You're happy if your neighbors are actually different from you, and represented as being x between 0 and 0.5. Half of your neighbors are different from you, and still simulate the these kind of models. And here you can see that more movement. And sometimes what happens, what I observed in my toy simulations with the students, is that you get these kind of lines of individuals of the same color if you specify their preferences as preference for variety. It's not completely mixed, it's mixed in a particular way. That's something you can get even from this very simple model. Now, for those who have mathematical background, these models are very known as cellular automata when I was a student, still felt like this. And from policy point of view, Jennings used it to study patterns of racial segregation in American cities. So it's a very simple introductory model, but I think it already contains most of the elements that most other models of agent-based kind that I've seen in economics. Some graphs I've already demonstrated to you. Now, moving to further sets of models that I wanted to talk about. One that I was working on, it's actually now somewhat abandoned, working paper we have from last year. It's a model that as economists, we often study markets. So we study market with buyers and sellers. And buyers and sellers, they have rules of behavior that are represented by, for example, go to a particular seller, or to seller 3 as a buyer. For a seller, it could be set price 10. For a buyer, it could be accept this price 10. And these rules have strengths, just numbers. And these numbers are updated in view of how well they perform. One day, one buyer goes to one seller, trades with the seller at a particular price, that gives the buyer particular utility. Then the buyer updates this rule in view of this utility, and similarly for sellers. When these agents, they choose the rule with the highest strength most of the time, but there is also noise. They can experiment with different behaviors. Now, this model from a mathematical or computer science point of view, known as reinforcement learning, simulates this, and the strength of the rules are reinforced in a different way. Eventually, it may converge. What we studied here is, do buyers become loyal to the same seller? Do they decide to go to the same seller most of the time? And that's what we observed. Well, first, we initialized the model again randomly. So there is a period of time when prices fluctuate a lot, but eventually traders learn to trade a particular price, and it fluctuates very little. And as a loyalty index, it's close to 1 if buyers go to the same seller most of the time. That's what indeed happens. At the beginning, buyers go to random sellers, but as time goes on, they go most of the time to the same seller. And then we vary parameters to see how this loyalty of buyers can be affected. So that's one model that I wanted to talk about that studies market. There is another one that I also find interesting. Maybe some of you know it. That discusses algorithmic collusion and price setting, where again, economic behavior is modeled by agents, in this case firms, and set prices. Depending on how price is set, if a firm set a lower price than previously, then it increases its demand and decreases demand for the other goods, modeled in a different way. But that's typical economic assumption. And then firms update, again, the strength or the expectation, what they can get from a setting a given price in view of what happened in the previous round, in view of what were the previous prices, given what profit they obtain. Again, they choose the price, they choose to set the price that they expect to get most, plus, again, some noise. It's again a variant of reinforcement learning known as Q learning. Computer science literature, I think, mostly. And it's used for finding optimal choices in dynamic programming problems. The policy implication of this is that use AI or this kind of algorithms for price setting, some of the online websites now do, may be bad for consumers because they learn to set a higher price than the competitive market would expect. And as an illustration that is here, so here this is a game between firms. This lower dotted line is a Nash equilibrium price that the firms supposed to, if they were not colluding. The upper dotted line is what is known as monopoly price. That is what the price would be if firms were behaving as one, maximizing total profit for them. What they observe in this particular case, in this particular simulation, is that the price that the firms set in their case is closer to the monopoly price than the competitive price. They partially learn to collude. And the reason they also illustrate here that the firms learn that if the rival firm lowers the price, then this blue firm would also lower the price next time. And then after that, the firms would realize that it's not a good profit anymore, and they would gradually return to the price they were setting before. So the firms learn this kind of behavior that lowering price is not a good idea. You should stick to the price that you've converged to. Now, these are the models that economists use. A couple of models that I wanted to mention related to what was discussed in this event. There are also papers in economics that try to model epidemics, for example, in this case with behavioral response. This particular paper, I take the standard epidemic models, SIR, SIS model, but what they add is the behavioral response that individuals in the model would choose the level of social activity to maximize utility. It's the economist's perspective, to maximize what you can get best, depending on the current infection prevalence. And they model then these choices, find that the higher the prevalence, the perceived prevalence, the less socially active people are. Economists are obsessed with equilibrium, so they found the equilibrium of this under this assumption. And given the equilibrium, then they can simulate a dynamical system of infected individuals. They are shared. And since they also look at networks, they actually look at how one can apply a policy to reduce social activity. But what I wanted to show is that what they have in their paper is without behavioral response, that is the standard shape of what happens in SIR model, but with behavioral response, with the awareness that you better reduce your social activity if there is a lot of prevalence pandemic epidemic in the population, then this prevalence of infected individuals becomes smaller but lasts longer. And a final model that I wanted to mention briefly, also related to the other topic discussed here in the event, is technology adoption, green technology adoption, where economists, this particular paper, again, model decision of firms, but they can be also applied to individuals. There is again a utility of firms in this case that depends on the firm's type and the current proportion of firms using each technology. And the firms, again, choose something that gives them a best utility, but with noise modeled by a random utility model that was mentioned a couple of times before. So here, from mathematical point of view, that's a stochastic process, a stochastic polar process. And they study how taxes or subsidies for different technologies affect their final outcome. Of what they have is that depending on the initial state of how many firms of a given type, whether they are preferring green or brown technology, and how many already adopted technology, they simulate this system and find that depending on the taxes and subsidies, these lines that define in different thresholds for different kind of firms can move, and then there will be more or less simulation runs that would sometimes converge to everyone adopting clean technology, sometimes not. They can study how often everyone adopts green technology. Now, the summary of what I wanted to demonstrate here is that in economics, most of the agent-based modeling used to show what can be called sufficiency theorem. There exists a model, perhaps simple, that can explain patterns that we observe, perhaps complex, of economic behavior. Agent behavior in these models are often boundedly rational. They look only what happened before and learn from what happened before, but not necessarily what they expect to happen. Optimization is often only in a limited sense. Noise is modeled very generic way. And also there is so far what I think is limited heterogeneity in the agent behavior there. And behavior is only loosely based on what is known about human behavior. It's, I think, what comes from the discussion that I participated in this event is that perhaps economists do need a better modeling of agents in their models. Thank you.